Hello, welcome to Fundamentals of Acoustics. Today is the 5th day of the 10th week of this course. Yesterday we had started our discussion on discrete Fourier transform and we had shared with you a relation which will help you transform discrete data in time domain into frequency domain. And the expression for that is shown here. So, that is the expression. And we had explained the importance of parameters n, lowercase x, k and uppercase k. And now what we are going to do is we have a signal and let us say that the signal is x equals 2 times sine of 2 pi ft and let us set f as 1 hertz. So, the actual signal is shown in green continuous line, but modern data acquisition systems do not acquire continuous data because they are digital. So, instead of continuous signal, what we are our data acquisition system is just getting points, and let us say we are recording the first 24 points, that is for a period of 3 seconds. So, I have these 24 points which are marked here. Now, what I want to do is I want to use this information for 24 points, and from that information I want to figure out the Fourier components of this signal, that is its representation in the frequency domain. So, with that let us look at some of the slides. So, this signal, the actual, so these are the points, so this is point number 1 which corresponds to n is equal to 0. So, this is point number 1 corresponding to n is equal to 0, this point corresponds to n is equal to 2 and so on and so forth, and this is the 24th point and the corresponding value of n is 23, which is equal to capital N minus 1. Okay. So, this is the actual data which we are getting, and now from these data we have to figure out the frequency domain representation of the signal. So, what do we do? So, first let us look at this table. We have explained that there are 8 points measured each second, right. Our data acquisition system, the way in which we are using, it is measuring 8 points every second. So, we say that our sampling frequency Fs is 8 samples per second. If it was measuring 16 samples, then it would have been 16 and so on and so forth. The other thing to note is that both n, so n is what? It is the index on time, and k, which is the index on frequency, they can assume 24 different values. Okay. So, in this table n is going down and it is starting from 0, 1, 2, 3, 4 till 23, and k starts from here and it is going in this direction. So, k is equal to 0 here, and I had said that when we compute xk, it will have a real part and an imaginary part. So, for each value of k, I have xr, which is the real part, and xi, which is the imaginary part. So, I have 2 columns for each value of k. One is, this column is the real part, this column is the imaginary part for k is equal to 0. Then for k is equal to 1, I will again have a real part and an imaginary part. So, in this table I have constructed this table which I will use to compute different values of xk, specifically their different values of xk, their real and imaginary parts, and we will learn how to do that. So, that is what it says here, xk can assume 24 different values from k is equal to 0 to k is equal to 23, and further xk need not be a real number, it can be complex, as the RHS of the equation which we had discussed earlier, it can have real and imaginary components. So, what we have in this table is a matrix, and here onwards we are going to compute different values of xk, and in the and n goes down, and it goes down from 0 to 23. The next column is time, the third column is ft. Okay. So, this is what there is. Now, we will learn how to do it. Okay. So, this is what we do. Okay. So, this is an illustration how for each value of k we can compute x k. So, first n is equal to 0 to 23, it has been listed here. Then at a given value of time, so when n is equal to 0, time is 0. When n is equal to 1, what is the value of time? We are measuring 8 points each second, right. What does that mean? It means that each second is divided into 8 different parts, which means that corresponding to n is equal to 1, this is 1 over 8th, t is 1 over 8th, which is 0.125 seconds. For n is equal to 2, it is 0.25 seconds, and so on and so forth. So, the final value of t corresponding to n is equal to 23 is 2.85 seconds. Okay. Now, this formula was already given, and what was this formula? So, for each time I have to know what is its value. So, what was the value? It was 2 sine 2 pi f t, and f was 1 hertz. So, for this value of time I have calculated the value of function. So, it is given here. So, this one, so all this data is given. From this given data, which we can measure experimentally, we have to compute capital X, right, xk's, x1, x2, x3, x4. So, that is what is shown here. So, these two columns correspond to k is equal to 0, these two columns correspond to, actually it is not k, but xk is equal xk, this column corresponds to x1, this corresponds to x2, this corresponds to x3, and so on and so forth. So, what do we do? So, we will explain that in the next slide. So, let us say we want to compute x0, let us say we want to compute x0, we already know the values of f0, f1, f2, f3 from this column. So, what is x0? This is the general relation xk equals xn, which actually changes with time, times, so what is this thing? This is e to the power of minus I omega k, what is that, k n divided by n, right. So, I can express it as a cosine term and a sine term. I can express this e I omega k n as a sine and a cosine term. So, what I have done is I have expanded this, and in this relation I have put k is equal to 0. So, when k is equal to 0, this expression becomes x0 equals sum of xn cosine 2 pi times 0 times n divided by capital N minus I sine 2 pi times 0 times small n divided by capital N. How did I get this? I use this equation, and in this equation I have put k equals 0, and then for different values of n I have summed this entire expression for different values of n, small n, and n changes from 0 to n minus 1. So, in that way I get x 0. If I have to calculate x1, again we go back to this equation and I plug in k equals 1. So, when k is equal to 1, I have 1 here, and using this expression I do the summation, this is the summation, and I get x1. Okay. So, in this way I have been able to calculate x0, x1, x2, x3 and so on and so forth. So, these two columns are for x0, these two columns are for x1, these two columns are for x2 and so on and so forth. And as I said, each x will have a real and an imaginary part. So, I have listed those here. and the sum. So, what I have done is here, this is the individual component corresponding to each n. What is the individual component? So, if n is equal to 1, then when I put n is equal to 1 in this expression, I get the first component, right. So, these are the individual components, and this is the sum of the entire column. So, the sum of the entire column corresponds to this operation, okay. And so, and then finally I get the magnitude of FFT. So, this magnitude of FFT, so this magnitude is basically this term square plus this term square and the square root of 2, square root of the sum of the squares. This is the real component, this is the imaginary component. If I square them, add them up and take the square root, that is the magnitude of xk. Similarly, for x1, square of this plus square of this and then add them up and take the square root, I get this is x1. So, the last row. This is for x2, this is the real portion, this is the imaginary portion, this is the square root of sum of their squares. So, that is x2, and similarly this is x3. So, in x3 what do we see? This is the real portion, this is the imaginary portion, and the sum of them is giving us x3, and so on and so forth. Okay. So, what does it tell us? X0 equals 0, x1 equals 7e minus 16, which is 0, x2 equals 5e minus 15, which is 0, x3 equals 24, x4 equals 0, and so on and so forth. So, what did we get? We got x0 is equal to 0, x1 equals 0, x2 equals 0, x3 equals 24, x4 equals 0, and it went on till x23, because there are 24 points. What does this mean? That the first frequency has 0 amplitude, second frequency has 0 amplitude, third frequency has 0 amplitude, but fourth frequency has an amplitude of 24. Now, this is not the real amplitude, as I mentioned earlier, we have to convert it into some real units. So, what is the real amplitude? The relation for real amplitude is given here. So, that is equal to xka, ka, a means actual. So, this is actual. This equals 2 times xk, this is the relation, 2 times xk divided by n is number of points. So, which means that x 0a equals 0, x1a equals 0, x2a equals 0, but x3a equals 2 into xk, x3 is 24 divided by number of points 24 is 2. Okay. But we still do not know that this x3a corresponds to how many hertz. All we know is that this is the fourth frequency in the system. First frequency amplitude, actual amplitude is 0, second frequency actual amplitude is 0, third frequency actual amplitude is 0, fourth frequency amplitude is 2. That is all we know. Okay. Now, we will figure out how do we compute the frequency of the system. Okay. So, but before we do that, this is an important thing to note. It says if we plot xk versus k. Okay. So, I am plotting xk here and I am plotting k on the x axis. Then at this location k is equal to n over 2 minus 1. So, let us say this is k is equal to n over 2 minus 1. This function, it will be symmetric. So, if it rises here, it will rise here. If it goes down here, it will go down here. Okay. So, at this location x k is equal to n by 2 minus 1, the plot of x k versus k will be symmetric. And typically we take data only from the first half or the second half, because all that data is symmetric. Okay. So, what we have learned till so far is two things. How do we calculate different values of xk? We have learned that, and from those xk we can compute the actual amplitudes of individual frequencies. But what are those actual frequencies, we do not know yet. So, in the next few slides we will learn that as well. So, this is the theme for the remaining portion. So, before we talk about frequencies, let us talk about this Nyquist theorem. So, there is a theorem developed by Mr. Nyquist, and he says that if there is a signal and let us say that signal has lots of frequencies, it may have 1 hertz, 2 hertz, 30 hertz, 40 hertz, 20,000 hertz, and if I have to capture all the frequencies which it has, so and let us say that the highest possible frequency in that signal is 20,000 hertz, then I should sample it at a frequency which is twice the maximum frequency in the signal, 2f max. Okay. So, if I think that my signal may have frequencies as high as 15,000 hertz, then my sampling frequency should be at least, it should be at least 2 times that, which is 30,000 hertz. So, that is what it means. So, another way to look at is that if I am sampling my signal at a frequency at a value fs, fs is sampling frequency, then the maximum possible frequency which I can extract from it is fs divided by 2. Okay. So, this is there. So, this is an important parameter fs, because when we calculate the actual frequencies we will use this. Now, in DFT we have actually 4 definitions of frequencies. Okay. First definition is known as normalized frequency, normalized frequency. So, how many frequency components we get if there are n points? We will get n number of frequencies, right, corresponding to k is equal to 0, k is equal to 1, k is equal to 2 and so on and so forth. Now, the normalized, so for the kth frequency, normalized frequency is defined as k divided by n. Okay. So, it will be 0 by n, 1 by n, 2 by n, 3 by n, and it will go up to n minus 1 by n. Okay. The second frequency, so we do not bother too much about this, it does not make a lot of physical sense. The second frequency definition in DFT is normalized circular frequency. So, if you just multiply this k over n by 2 pi, this is your normalized circular frequency, and the actual frequency is k times fs divided by n, it is k times fs divided by n. So, in our case what is the value of fs? In our case fs was 8. So, k 0, 1, 2, 3, 4, 5, 6, 7, 8 and so on and so forth. Actual frequency, let us call this f actual. So, let us compute f actual. When k was 0, f actual means 0 hertz. When k was 1, it means 1 times 8 divided by 24 is 1/3 hertz. When k was 2, 2 times 8 divided by 24, it means 2/3 hertz. When this was 3, it is 3 times 8 divided by 24, it means 1 hertz. Okay. So, the moment we know k, using sampling frequency and the total number of points which we have collected, we can calculate actual frequencies. and we have already learned how to calculate the actual amplitude using this relation. Okay. So, we know now how to calculate actual amplitude, and we found that actual amplitude for the fourth frequency was 2, and that corresponds to a frequency which equals 1 hertz, and that is exactly what our result should be, because what was the original signal? The original signal was 2 sine times 2 pi ft, right. So, the frequency was 1 hertz which we have calculated, and the amplitude was 2, and the last thing is phase. We can also calculate the phase of this signal. Now, what is the phase of this signal? Phase, theoretically, it is what? Huh? So, let us look at, so the imaginary component was 24, real component was 0, right. So, tan inverse 24, no, actually sorry, it is minus 24. If you look at where is that? This is minus 24, imaginary component is minus 24, real component is 0. So, from this you can compute the phase also. So, now you know how to compute phase for each frequency component, how to compute its amplitude. The amplitude can be calculated by first constructing the table and then using this xka equals to xk divided by n, and then the corresponding frequency can be calculated by using this relation. Okay. So, I think that all this information is sufficient for today's lecture. We will meet once again tomorrow, and we will discuss some other features of DFT, so that when you actually acquire data, you can you know how to correctly acquire data and how to use it effectively. So, with that we close the discussion for today, and we will meet once again tomorrow. Thank you.